Hi, and welcome back to another extreme value theory video. In the last two videos, we considered how the block maxima, peaks over threshold, and point process representations of extreme values are impacted when our underlying process is not IID, but instead is a stationary process following the asymptotically independent maxima condition. In this video, what we're going to consider is how, under the same conditions, our approach to statistical inference is impacted. This first slide gives a general overview of the workflow for modeling the extreme values of a stationary process. The first step in our analysis is going to be to identify independent clusters of extreme values, and from each cluster to extract the cluster maximum. We can then model those cluster maxima using a GPD distribution with parameters sigma u and psi, and use these clusters to estimate the extremal index theta. If we're not interested in the maxima, the largest event within each cluster, but instead we're interested in modeling all extreme events, we then need to adapt these results so that they describe all exceedances rather than just the cluster maxima. Finally, what we need to do is go back and check that the results of our analysis aren't overly sensitive to our choice of extreme value threshold or the declustering method that we've used to obtain our clusters in the first place. For the rest of the video, I'm just going to walk through each of these steps in a little bit more detail. So our first activity is going to be identifying independent clusters of extreme values. There's lots of methods for doing this, so what we're going to do is focus in on a method called runs declustering, and this has only a single tuning parameter m, which takes a non-negative integer value. We're going to say that threshold exceedances belong to the same cluster if they're separated by less than m consecutive non-extreme values. This takes a little bit of thinking to get your head around, so what we're going to do is consider this example process for a range of values of m. If m is equal to 0, then each threshold exceedance, so each value above this line shown in red, is going to form an independent cluster. So each cluster is of size 1. If m is equal to 1, then threshold exceedances belong to the same cluster if they're separated by less than 1 non-extreme value. So what we would have in the case of m equals 1 is 3 clusters. We'll have the first 2 clusters containing a single observation, x2 and x4, and a third cluster containing both x7 and x8. In the case of m equals 2, then threshold exceedances belong to the same cluster if they're separated by less than 2 consecutive non-extreme values, and so we get 2 clusters of size 2, the first one containing x2 and x4, the second containing x7 and x8. And finally, if we've got m equal to 3 or more, then all of these 4 extreme values are going to be allocated to a single cluster. Great, so I hope that's helped build a little bit of intuition about how this declustering method works. And once we've identified the clusters using an appropriate value for the threshold u and the declustering parameter m, then we can extract the maximum value for each cluster to proceed with our analysis. We can estimate theta hat using an empirical estimator. So all we're going to use here is the empirical probability, so the probability within our sample, that the maximum of the next m observations is less than u, given that our current observation is a threshold exceedance. What it turns out as is that this estimator, theta hat of u and m, is simply going to be the reciprocal of the expected cluster size when we're using this runs method to decluster our data. So theta hat of u and m is going to be the number of clusters above u that we identify, divided by the number of threshold exceedances of the threshold u. And what's important to note here is that this estimator is going to depend on what we choose for our extreme value threshold u and our runs separator m. And if you'll recall from a previous video, our actual extremal index shouldn't be dependent on this threshold parameter. This gives us a way of checking if we've set u to be large enough and set m to be large enough, because this estimate should be stable for large enough values of the threshold and the separation parameter. So here we're considering the daily returns of the S&P stock price data. And we can see that for thresholds above approximately 0.03, our estimated value of theta levels off and becomes stable for all values of m, and that for values of m of 5 and greater, we end up with a similar estimate for our extremal index, somewhere around 0.5. So this gives us a way of obtaining a point estimate for our extremal index theta as the observed number of clusters divided by the observed number of threshold exceedances. But how can we assess the uncertainty in our estimate? In doing this, we've got yet another bias variance trade-off coming up. So if we're picking u and m to take large values, then we're going to get fewer smaller cluster sizes, and these clusters are more likely to be independent of one another. However, if we pick u and m to be smaller values, then we're going to end up with more clusters with more exceedances per cluster. And what that's going to do is lead to smaller sampling variability in our estimate to theta hat. However, our observed clusters are less likely to be independent of one another. So we've got to strike a balance between picking u and m large and u and m small. When we're calculating the standard errors of this estimator, then we can't just appeal to our usual approaches because our observations aren't independent of one another. Instead, what we have to do is use bootstrapping methods to resample blocks of threshold exceedances and use these to construct the empirical distribution of the sampling distribution of our estimator theta hat. So once we have our estimates of our level of clustering and what our clusters are, we can then use our identified clusters to extract the cluster maxima and fit a GPD model to these. If we're only interested in the distribution of cluster maxima, we can stop there and use standard methods to estimate the standard errors of sigma u and psi. But if we're interested in describing more general extreme values, so all values exceeding the threshold u, then we need to use bootstrapping to obtain these standard errors, again because our observations aren't independent of one another. If it's not a peaks over threshold analysis that we're interested in, but instead a block maxima or a point process representation that we're wanting to estimate, then we can estimate the parameters of those models by equating sample and model properties. What this gives us is that the GEV scale parameter, sigma, can be estimated by the GPD scale parameter multiplied by the number of clusters above u raised to the power of the estimated shape parameter. The location parameter for the GEV or the point process model is given by the GPD threshold. Add the difference in estimated GEV and GPD scale parameters divided by the estimated shape parameter. Again, if we're interested in obtaining confidence intervals for these parameters, we're going to have to use bootstrapping methods to do that because of the dependence of our observed data. And the final step in our analysis is to use these parameter estimates to construct quantities of interest, such as return levels. And what we have to do is assess sensitivity of these estimates to our particular choices of extreme value threshold U and declustering parameter M. So the actual process of doing this is very simple. We just have to rerun the analysis with a different threshold and a different declustering parameter. But the tricky part in this is defining exactly what is meant by the results of our analysis being materially altered. How big can the difference be before we really care about it? Great, so that's all I had to run through in this video, and thank you very much for your time, and I will see you in the examples class on Friday, where we'll look at implementing some of this. Thanks.